It seems like uh, you know my live stream might have uh, started to work correctly now. If it is not, just let me know and we can take it from there. So uh, so yeah, I think it is correctly working now. I really apologize for the fumble in the first 10 minutes of my talk today. And I hope and believe that everyone, whoever is interested, is now able to join the talk, and then we can take it forward from here. So, welcome everyone for with respect to today's talk. So, let me share my screen about some of the things which we wanted to do today. So, here it goes. So, basically, for today, what we wanted is to kind of go through the machine learning element formulation in terms of not going through the exact formulation because that will go into the IP side of things, but at least show what we have been working on with respect to machine learning and showing the finite element equivalence, if you will. So, so in terms of today's lecture, what we will be covering is basically, as we discussed in the previous lecture, that we that for example, if we have the brick element, for example, the eight-noded brick element, and there are various integration schemes of the brick element. Again, let's say we are interested in one of those integration schemes. And for most cases, until and unless you have, for example, a magnetic material or a frictional case where basically you're looking at, uh, you know, frictional coefficient which is extremely high, or some of those some sort of those cases, your finite element matrices will be unsymmetric in those cases. But for the most cases of engineering analysis, your finite element stiffness matrix is symmetric in nature. So let's say we are talking about 24 doves, and basically for 24 doves, you will have 24 rows and 24 columns. But then, if you preserve the diagonal uh, over here, then we are talking about 300 entities, because you can look at them as n plus 1 over 2, and you are going from one entity to 24 entities. 24 times 25 over 2, 12 times 25 is 300. So you have 300 entities which you need to take care of. Not only that, the other aspect which you need to kind of ensure is that, for example, at least in the elastic part of the problem, there will be 24 eigenvalues, and in the first 24, the first six of those eigenvalues should go to zero, because of the obvious because of the obvious um, uh, modes which have issues with respect to uh, deformation, which do not really contribute uh, uh, to the shape change of your element, so to speak. So those first six eigenvalues should go to zero. So basically, those are the two conditions to start with, about which we have to kind of start looking at the problem. The symmetric aspect of the problem can be taken care of in terms of just looking at the 300 entities, for example. But again, for the unsymmetric problem, this will change. And again, I'm not going into the details of that. But then, for example, with respect to 24 eigenvalues as well, we have to be extremely careful in terms of how we can ensure in all cases that the first six eigenvalues go to zero. So again, the first six eigenvalues being going to zero, again goes into the IP part of the problem. But these are the two conditions about which we have to create a matrix and basically show that when we predict a new learning based matrix for deformation with respect for example, we are looking at for example, we have different different distortions of this particular element available, and its k matrix available, which is 24 plus 24. uh, Basically, in certain ways, we have satisfied for both the conditions, and then basically you have to figure out for a new condition where, for example, one of these edges has moved by a certain distance. This node has moved by a certain distance. The face on this other side has become distorted or something like that. That basically for a new configuration of this particular element, your K matrix is repeatable to a very good accuracy with your machine learning prediction. And that's basically is what we capture through the machine learning algorithm we have. And then basically, for example, I wanted to show you uh, a couple of examples with respect to that. What actually happens in terms of the result is that, if I can go to these particular slides. So yeah, basically what happens in this particular scenario is that if you look at the stiffness matrix so basically, I mean, considering those two conditions which we just talked about, the um, upper triangular matrix and the six eigenvalues going to zero, what we see is that by putting our machine learning algorithms in, um, for the new case scenario for which we were just talking about, for example, we move the node of move one of the eight nodes to a different place, change one of the faces in a different manner, change another edge in a very different configuration. Then what we see is that basically for the new matrix, k new on the on your y-axis, k nu being the finite element stiffness matrix, and on your x-axis, k being your machine learning stiffness matrix, still gives a very good accuracy match between the two cases, meaning the numbers lie on this 45-degree line, which kind of shows that the accuracy is very good in between the two case scenarios. Not only that, if you solve, so basically, if you kind of arrest certain degrees of freedom, and let's say you are pulling on the z direction, um, or on some other particular direction, we have done a lot of cases where we change the boundary conditions appropriately. And what we see is that if I mean, e- even for example, if the stiffness matrix has certain mismatch which we cannot see, for example, through our naked eye. If, for example, we would have changed the displacement in if we have changed the boundary condition, um, if we have kept the boundary condition in the finite element case and the machine learning case to be exactly equal to one another, basically we should have gotten the same result, and that's what we are seeing over here. And this again reconfirms the case that even if the finite element matrix is exactly is very very close to its finite element counterpart, we see very very good match with respect to displacement as well. Now, this is only the case for one element. You can repeat the case with traditional assembly for many more elements as well. Once you have gotten the basic formulation for the machine learned element, and you will see similar type of mismatch, similar type of match in between the finite element and the machine learned element. Now, as I was talking about the six eigenvalues over here, you can see that for the six eigenvalues, this is um, the machine learned stiffness matrix. This is the actual stiffness matrix. You can see that in our algorithms, we not only ensure matching of the stiffness matrix, we also ensure matching of the eigenvalues by not actually finding out the eigenvalues. So, so basically, in the training algorithm, there is, uh, um, uh, you know, there are some aspects of it. But for example, in the prediction case, you don't find the eigenvalues. You just predict the actual stiffness matrix, and from that actual stiffness matrix, from that machine learned actual stiffness matrix, you directly get the six eigenvalues to be zero, which is very similar to the actual stiffness matrix. And for the non-zero matrix, for the non-zero components of these eigenvalues, what you can see is that there is a very close match in between these eigenvalues. So, for example, for this particular case of a brick element, you'll have 24 degrees of freedom. So if six of those go to zero, then for the other 18, you can see that the match in between the eigenvalues is very close. And when we plot these eigenvalues, again in a XY fashion, X being, on the x-axis, you're plotting the machine learning and enabled stiffness matrix eigenvalues, and on the y-axis you are plotting uh, basically the actual stiffness matrix coming from finite element eigenvalues. You can see that they lie on a 45-degree line. And so that becomes very clear that for cases where you are not actually trying to solve a finite element problem, but actually a for example, a materials problem where basically your constitutive formulation is of higher importance compared to the element formulations. Maybe those cases, for a very close accuracy in between the finite element stiffness matrix and machine learning stiffness matrix, there is always a choice, which one, choice or a decision one can make, uh, basically playing with either the machine learning component of the stiffness matrix or the finite element component of the stiffness matrix. Again, we will be presenting one paper with respect to all the research which I just showed to all of you today in our TMS article, in our TMS presentation next year, where we'll be talking specifically about this particular research and basically how we can get a very close approximation of the solution based on the machine learning counterpart of the finite element, of the finite element, so to speak. Now, for the assembly part again, so basically this kind of explains again what we are here to do, what basically the machine learning counterpart enables with respect to the finite element portion, with respect to the finite element stiffness matrices, if you will. And basically it also shows the power of machine learning where, for example, if you're not uh, of course, as you can see over here, there is a small difference with respect to the eigenvalues in the non-zero areas, but for the most part, uh, attainment of all the six eigenvalues going to zero, and the error is actually very less, to the fact that most of the eigenvalues are there on the 45 degree line. Actually, all of them are on the 45-degree line, and on top of it, basically the error is actually less than 1 e power minus 2, 1 e power minus 3, and in certain cases, even the error is less than 1 e power minus 8. So, depending on the amount of data set you have available, you can actually play with the error. And of course, since this is a one-time training which you will do for training that particular element um, uh, for that particular integration scheme, so to speak, which will tie up with your elasticity simulation or its plasticity counterpart. That will be a one-time affair. So basically, that opens up many options with respect to what you are setting out to do. Of course, again, as I was telling you earlier, if the entire problem is stuck at if the element formulation and the integration scheme is of utmost importance, you might want to carry on with the utmost accurate element formulation which comes through finite element. But then if for example you care, for example, 99.999% correct answer, but then with respect to your other objectives, such that you want to capture a much more complicated continuum law, for example, that might be these type of machine learning approximations could be looked at for these purposes, so to speak. So again, in a nutshell, I would like to go through the results again. There is a good match in between the finite element counterpart and its machine learning counterpart in terms of the actual stiffness components, those 300 components which we were talking about in the upper triangular matrix. Followed by the displacements. Basically, they match if you put a certain type of boundary conditions. The displacements obtained through the finite element method and the displacements obtained through the machine learning uh, element method are one and the same, and this could be repeated again for other type of boundary conditions, so to speak. And then the the third aspect being six of the eigenvalues going to zero, and then for the non-zero eigenpart and non-zero eigenvalue part of the problem, the eigenvalues being very close to one another. So this basically tells kind of communicates to our customers, and for people who are setting out to do some research in this direction, is to kind of figure out some innovative ways in which we can actually talk about how finite element finite element methods can take advantage of machine learning technology, so to speak. The most important part is we are not changing the way traditional element formulations have the power of creating that stiffness matrix. Nor are we changing basically any of the other constructs that after you create a machine and after you create an element, you have to kind of assemble them, and then once you have assembled them, then you have to solve for the global solve for the global problem under certain boundary conditions after shortening the matrix, if you will. But the entire premise of the idea resides on the fact that none of the assumptions of how traditional finite element is done has been changed, but we are just bringing machine learning element to the bear, where basically if you have more complex constitutive laws, you can also look at element formation or assembly in some newer ways, if you will. Now now talking about, so basically what we have discussed so far is basically how what kind of things we have looked for. For example, for the solid 185 element, we have looked for the upper triangular matrix and the eigenvalues as the major driving force of how to bring machine learning to bear. But then now we will start looking at basically how to assemble finite elements, if you will. So in traditional matrix assembly, if you look at it, mostly mostly it is done through chunk by chunk or element by element assembly, where basically you have the connectivity matrix, and then basically the connectivity, based on that connectivity matrix, we figure out if this node has connectivity with respect to this element and some other element, and based on that, we assign contributions of the local element stiffness matrix uh, towards global counterpart, if you will. But doing so, and doing so has been very, very successful. And in the past 50 to 70 years, when people have been working on finite element assemblies and things like that. But again, this problem can also be looked at from, for example, a Tetris example. I believe many of you who have played the game of Tetris know that various pieces of Tetris come into contact with one another in a step-by-step fashion. So I'm going to kind of share a website with you all to kind of look at this particular aspect. So maybe, yeah. So if you look at this, and I hope and believe that this is visible to you all. So basically, what's happening over here, and this is on a game break maybe. So you can see what's happening over here. So this is 3dtetris.com, and you can see that over here, you know, different chunks. And this is a very simple case scenario where all the element faces are straight, the edges are straight, and things like that. And you know, random chunks of material are coming from the top, and they kind of getting stuck to one another. And basically, if the entire surface gets covered with respect to its previous element, then that entire surface goes away. But if you look at it, you know, doing element assembly in chunks might be an alternative proposition which can be looked at. And one of the ways, so yeah, enough of this particular website. So yeah, you can certainly look at this website if you're so interested. And basically, what it is doing is nothing more than uh, basically showing how different chunks of elements kind of come together and get joined together or get enjoined together, so to speak. But why I showed you that particular website, and then again, let me share I went oh, so I have so let me share my window. So basically, if you look at this entire problem, uh, of matrix assembly or stiffness assembly, so to speak. And again, I will not go into terrible details of how basically you can exhaust all possibilities of elements coming together in different ways. But basically, it's very simple for anyone to understand that elements uh, get assembled when elements get assembled when either their vertices merge with one another, or their edges merge with one another, or their faces merge with one another. So the entire idea is, if you have an n-dimensional element, uh, a merger is possible from zeroth dimension vertex to n minus one dimensional face, for that matter. So basically, there are a certain number of combinatorial options, And let's say if we are looking at a very simple example for that matter, what you have to first understand is what kind. So if I'm looking at 2D counterpart, for example, again, you can also look at a 3D counterpart. But for example, if I'm looking at a 2D counterpart, so basically, there are different features. One is this vertex, one is this face. One could be not a face, maybe edge for this matter. But on the 3D element, you'll have faces and things like that. So basically, first of all, we need to find out, how in how many ways this edge can be shared between other elements. So basically, to answer that problem, there are many possibilities that this edge will be shared with respect to other elements. And uh, one simple thing, one simple example of looking at this will be that at the end of the day, if you're looking at this particular point, the if you're looking at 2D, then basically the angles should add up to 360 degrees. Now you can also think about how the you know how what kind of constraints will be there for the edge. If you're looking at 3D, what kind of constraints will be there for the faces and things like that. So there are many of these constraints which one has to look at, and basically based on those constraints, one can figure out an optimization problem by which you can figure out various entities such as vertex and edge and face, and different ways these things can interact with other other with features of other elements. So basically, at least from an architectural point of view, what we were looking at is first figure out all the features. Those could be vertices, could be edges, could be faces, whatever. The idea is you have to have n minus one dimensional features compared to, for an n dimensional element you have to have 1 to n minus one dimensional features, if you will. And then basically you have to figure out when different types of constraints which will make any of the mergers possible, how many of them will be coming together and things like that. Then once you have those point based constraints, edge based constraints, phase based constraints, basically the map, how these elements are going to come together. And then basically you have to figure out a learning based method in which these constraints could be fulfilled. And basically there are only few ways certain constraints could be fulfilled. So machine learning is pretty efficient in figuring out what are those ways these constraints would be fulfilled with respect to independent features of different elements. So basically every element has its own set of features, namely the vertex, edge, face, whatever. And then on top of that, you impose different types of constraints which make the merger possible. And then basically, instead of doing it in a traditional sense, you can do it in a machine learning sense. And then that will give you, again, like you get in terms of map from your local node numbers to global node numbers. You will directly get k local to k global map. Rather than going through the node numbers, you will probably get like a how that local matrix, in what ways either it gets split or it gets assembled. Its contributions are either getting split first, and then basically how those split contributions are then getting assembled. So various ways of looking at it. It kind of opens this entire graph theoretical architecture, which will enable the possibilities in terms of how these different k local matrices and their different combinations can work for different type of geometries, if you will. and then that will feed to the K global matrix. And then once you have the K global matrix, you can of course put your boundary conditions and solve for the problem. Or, for example, I have looked at it from a serial memory parallel point of view, or in terms of the machine learning of assembly, but then with respect to distributed memory parallel and other aspects, that might be also possible, that you are doing your K local to K global transformation in different subsections of the global part, if you will. The other part, which is very interesting, is basically the thing which I was talking about earlier, that if for example the geometry of the edge changes, or the vertex changes, or the face changes, we have a direct way now for a certain element to figure out, based on change of the geometry, and then similarly for the change of the material. I have not gone into the plasticity side aspect of it, but we'll go into the plasticity aspect of it probably in the next lecture. And then maybe I will call it a day with respect to our LinkedIn lectures, and then have a more detailed session on these particular ideas in an advanced course. That may be a discussion for another day. But let's say, we have certain ways of figuring out, let's say, based on changing the geometry of this particular element, how the stiffness matrix could be obtained, and based on that stiffness matrix, how that stiffness matrix can get assembled, and things like that, which I was explaining just earlier. But it can also happen that you don't want to just get the stiffness matrix of one element, but let's say a group of two elements together, or three elements together, and where basically this edge can have n number of possibilities. This face can have, I'm just drawing a two-dimensional diagram, but it is also true for the three-dimensional diagram. So you can understand that all the eight vertices can have different configurations with respect to each of these elements. All the 12 faces can have different combinations, and then all the uh, all the six faces have different configurations. But then since they are assembled, of course you're not looking at four times all of those, but after assembly there will be a certain number of faces, because certain faces will be already assembled to one another, and things like that. And then basically the problem gets shifted in figuring out optimal packaging. So meaning, for example, if you have a certain geometry, then if you can figure out what is the optimal set of elements. So basically, let's say if you break down the entire assembly of that element into super elements, and then basically not figuring out the element assembly but super element assembly in one shot, that becomes another possibility of this approach. So so but but, but again, these possibilities where uh, uh, either you are looking at unassembled matrices, and I showed you some example of unassembled matrices, how the displacements match, how the stiffness matrices match. And basically once the stiffness matrices and displacements match, of course it's a done deal. But then we also went ahead and showed you not only that, but the eigenvalues match as well. So those are important pointers. On top of that, we also talked about how to look at features, different features of certain elements. For example, you have vertices, edges, faces. For example, for a 3D element, then you have to kind of look at different constraints. So I will just give a very simple example. For example, around a vertex, whatever elements come together, they should have like a 360 degree. But then that is only a constraint in 2D. In terms of 3D, that constraint will become even harder. Again, edges will have their own constraints. Faces will have their own constraints. You have to also worry about the normals, tangents, and things like that. So there are only certain possibilities in these, in which the features we have can be merged together. And those certain ways are probably a bit easier to figure out using machine learning methods. And once we have figured out those possible combinations, maybe those machine learning methods start, yeah, and then you can probably get a direct transformation of your k local into k global in certain ways, so to speak. So that basically is to give you an idea how we go, not only from not only we have certain ways of figuring out basically the quality of an unassembled element, but once that quality has been ascertained based on the features, how we can put things together. And then once we have put things together, maybe certain geometries uh, in engineering analysis, we have a certain chunk of elements which instead of calling one element at a time, or five elements at a time, or 10 elements at a time, maybe one chunk of certain element can be called, and then in its pre-assembled format, and instead of calling for the stiffness matrix of an unassembled element, maybe stiffness matrix of that smaller assembly uh, in different permutations and combinations could become function could reside in a certain database. That makes this discussion even more exciting. That that gives the reusability of of these chunks again back to the geometry. And once basically that geometry is calling different sections of the matrix, based on that we can call whatever is necessary. And then this is also very useful from the point of view of, let's say, if you're doing analysis where certain portions of the geometry have higher amount of nonlinearity, whereas certain portions are deciding is still in the elastic regime based on your constitutive law and integration scheme. That that portion of the supergeometry, uh, that chunk of the element could have that elastic property, whereas the other chunk could have a nonlinear constitutive law in it. And basically, then we can look at how for example, in terms of crystal plasticity, how that deviation would occur in terms of either an unassembled element or pre-assembled chunk of elements, so to speak. So basically, uh, in the next lecture, what we will talk about is, so we talked about the unassembled element, single element, and basically how we can reproduce different aspects of it, such as stiffness matrix, quality of displacement results, quality of eigenvalues, and things like that. But going forward, we would also demonstrate, maybe in terms of crystal plasticity, how the eigenvalues kind of deviate from its elastic counterpart, and whether that could be captured or not. So basically, that will show for that particular unassembled element whether uh, whether if you change the material law from elastic to nonlinear, to nonlinear crystal plastic, how the deviation of the stiffness matrix would appear. We will compare and contrast that deviation against against a continuum plasticity material, if you will, and that will show basically why scale dependent laws are important in assessing correct physics, as it lies as it lies, and has to be correctly reflected with respect to what you want to kind of capture, what kind of physics you want to capture for what type of length scale. And then we'll also talk about some results where basically, as I was talking about, that's at certain times like Tetris, you may not be interested in, for example, one element at a time, but certain chunks of elements. And then that becomes very interesting, because if you look at even your grain boundaries, uh, for example, in certain hotspots, you will have to have a very informed law, for example, crystal plasticity law. But for other, so for example, in this particular regime, you might want to have a very highly informed nonlinear crystal plasticity law. But maybe these regions over here can have a continuum plasticity law, and then these regions which are further away can have fully elastic regimes. So basically, how to kind of tie these different regimes together so that correct physics is reflected, and then you can tie uh, uh, different different pre-assembled building blocks, if you will, um, instead of computing it through finite element, maybe computing it through machine learning. Some of those examples will be covered in the next couple of lectures, if you will. And then this entire overview might be taken, might be consumed into a very advanced course, which we can offer through one of the ANSYS podiums. So, thank you for your time today. I apologize for the first 10 minutes of fumble. I was not very sure whether my mic is working or not, but now since it is working, I'm glad that I was able to spend some time today with you all. For paying customers who work with Answers, if you have any questions about any of the concepts, of course, um, uh, you can contact us about this ongoing research. And basically, there will be a paper on some of these concepts, and basically the results of this analysis with respect to different material laws and how it can reflect reality in a much more reflect reality with respect to experiments in next TMS. So look out for our paper in TMS 2024, which has also been accepted for presentation, where we will show some of the results from this type of analysis. Again, thank you for your time. And I hope and believe that even if you're not a paying customer of Answers, if you have just an overview question, please reach out to me. My email ID is dipankar.pal@answers.com. And the reason why I'm sharing this with you, because at Answers, we also learn from students. Of course, paying customers are the source of income for Answers, but then again, researchers such as me, we also learn quite a lot from students who might have had their own ideas about some of these, some of these from some of these overview ideas which I shared over here. They might have their own ideas which they want to try out through our Answers platforms, such as PyAnswers, Mechanical, or APDL. So I want to have those conversations with you all, and that's why some of these lectures are also in the open format in LinkedIn, because not only these are requested by some of our customers, but also it provides us with ample opportunity to connect with like-minded individuals and students who might have a better idea with respect to this, and we would like to, of course, listen to them. And if their idea is worth enough, then maybe try out that idea with respect to our Answers platforms if they're willing to share. Uh, so basically, that is all for today, and thank you for your time. Hope you all have a good night, good morning, or good afternoon in different parts of the globe. And yeah, let me know if you have any questions or concerns, or have a good idea which we definitely want to kind of hear from you all. Thanks for your time. Have a great day. Have a great night.